Okay, so today we're going to be talking about section 12.5, and 12.5 is equations of lines and planes in 3D. So the first thing to note, or the first thing to remember, is what did we do for the equation of a line in the xy plane? So now when we write xy plane, we mean just two space where here's your x and here's your y. And remember back when we were just dealing with two dimensions, if we wanted to describe or give the equation of a line, we just needed two pieces of information. One would be a point, right? A point on the line, and the second would be the direction of the line. And the way we gave a point would be x naught comma y naught. And the way we gave direction would be to give slope, right? So slope kind of gives you the direction that the line is pointing, right? The angle of inclination. And then we had a formula, y equals y naught plus m times x minus x naught. Okay. And this was the point slope form. And I just want to mention that we also have about three different ways that we can express the equation of a line. We could use the point slope form. We could also use the point form, right? Y naught, y1 minus y naught over x1 minus x naught, x minus x naught. And then we have the slope intercept form. And we're going to have the same multiplicity of forms in 3D space. Okay, so we'll have three different ways to write equations for a line in 3D space. Okay, so here we go. In this section, we will learn how to define three-dimensional lines and planes using vectors. So that's probably the brand new thing here, is that we'll be using vectors and not just points. Okay. So a line in 3D space is determined when you know a point, x naught, y naught, z naught, on the line, and the direction of the line. So what we're doing here is everything that we're talking about here is going to involve L is our notation for the line. So what we're saying here is that we need to know the direction of the line, and we need to know a point on the line. Okay? And of course, we're in 3D space, and what gives us direction? Vectors, right? Because vector includes magnitude and a direction. So if we want to describe a line, and we need in 3D space, and we need direction, we can just take the direction from any vector, right? That's parallel to the line that we are trying to describe. Okay, so let V be a vector that's parallel to L. And suppose you have an arbitrary point, P, on the line L. Now, from this, we can form the position vectors, P naught and P. Okay, so R naught is going to be the position vector of P naught, and R is going to be the position vector of P. And here, O refers to the origin. So we're talking about the point that is, so here we are, if this is X, Y, Z, and O is the origin, then P is an arbitrary point. Say this is our line, right? And so if this is P, then we've got a vector from O to P, and this vector has a position vector of, we want to refer to it as R. Okay, so R is our vector from O to P with the tail at O and the tip at P. Okay, so that's just the notation that we're using. And now this gets a little more specific. We're saying that if A is a vector that goes from, so A goes from P naught to P, okay, then we know that R, so here's R is in blue, R has to equal R naught, which is the position vector of that point P naught, plus A. Does that make sense? So R naught, right, plus A gives us R. So that means that for every point P that's on the line, its position vector R satisfies R naught plus A. Okay? But now, since A and V are parallel vectors, remember we said that V is going to be down here. V is a vector that is parallel to the line that we're trying to describe. So there's V and there's L. And we know that parallel vectors have to differ just by a scalar. So that means that A must be a scalar multiple of V. So that's written right here. So if A is a scalar multiple of V, that means that there exists some scalar T. So T is some real number. And A is the scalar multiple of V. So we can put this all together. And remember, so we've got two facts. So we've got that R has to be equal to R naught plus A. But we also have that A is equal to a scalar multiple of V. Putting these together, we have a vector equation of our line L. Okay? So just as a reminder here, what is R? R is going to be the position vector that goes from the origin to any point P, right? So P could be here, P could be back here, right? So P is varying, and R represents the position vector. The tip is at the origin, the tail is at the origin, and the tip is at that point P. R naught is the position vector of that specific point P naught, and V is the direction of our line. Okay, so these are the equations you want to make sure that you have. As you write this down, this is a big deal here. Okay, so this is the vector equation of the line L and the direction of L. So direction of line L is V, and line L goes through the, contains the point X naught, Y naught, Z naught, and R naught is the position vector X naught, Y naught, Z naught. Okay. So just a few comments here. What happens, because remember here T varies, right? So T is any scalar. And the idea is what happens as you vary T. Excuse me, T is a parameter. When T is equal to 0, then we're talking about the position vector R naught. If T is positive, now, right, keep in mind here, we're adding vectors. So let me actually kind of rewrite our formula here, which is R is equal to R naught plus T times V. Okay, so now V is supposed to be the vector that gives us the direction. So if this is V, and now if we take a different color, now T times V is going to be a scaled version of it, right? So imagine if we wanted T equals 2. That means we need the vector to be twice as long but in the same direction. So this will now be 2V. And if I'm going to add R naught to 2V, right, then I would create that parallelogram, and what's in the middle, that would be my vector, my position vector R. Does that make sense? And so when T is negative, that means that you're looking at V, but it's going in the opposite direction. Okay, so your position vector is now going to be behind, if you will, behind T equals 0. And you can think of T as time as well. So you can think of it when T is equal to 0, your R is giving you a vector based on the parameter t. So when t is equal to 0, your initial vector is that r naught, and your vector changes with time, but you could have positive and negative time. Okay. Okay, very good. All right. So we just said this right here. Positive values of t correspond to points on L that lie on one side, and negative values correspond to points that lie on the other side. We said that.
It's 2130.
Thank you. And then, so we're still working with our vector equation. We're saying that if a vector v, which was the vector that gave us our direction of the line, we could write that vector v in terms of components, right? And if we do that, now, remember we've got our vector equation, which is r is equal to r naught plus tv. Well, t times v looks like this, ta, tb, comma, tc. So we would have, what are we using for? So we'd have x naught. So now if r naught is x naught, y naught, z naught, then we would have x naught, y naught, z naught plus ta, comma, tb, comma, tc. Okay. And so we've got x naught plus ta, comma, y naught plus tb, comma, z naught plus tc is equal to r. So this gives us our components for r. Okay, because if we want to write r, we could write r as x comma y comma z. And this now tells us that x has to be x naught plus ta, y has to be equal to y naught plus tb, and z has to equal z naught plus tc. Okay, so this is what we have right here. Right, so we're just writing down what we wrote on the page before. And this gives us another way to describe a line with equations. These are called the scalar equations. So the first one that we had was a vector equation because the output was a vector, the input was a parameter t, and the output was a vector. Now we have scalar equations because the input is a value t, right? So we still have the input is a scalar, a parameter t, but the output is now going to be three different things. It's going to be your x component, your y component, and your z component. So this is another situation where you want to make sure that you write down this formula. Okay, not like that. Write down these formulas here. Okay, all right. So again, these are scalar equations, and we just did a proof that shows they are equivalent to the vector equations, the vector equation. Let's see here. Now, these scalar equations are called parametric equations as well, because the equations are all connected via the parameter t. Okay, and each value of the parameter t gives a point on the line. Okay, whereas with the scalar equation, each value of the parameter gives a vector, a position vector, with the tail at the origin and a tip on the line. We're now having an equation where the output is a point on the line. Okay,